You guys know I always like to try and do this, so I apologize if it's getting slightly tiresome, but for some of you, maybe lots of you, I actually hope you enjoy this part of the lesson. Often in maths, you will go do a bunch of things, you'll draw stuff, you'll write a whole bunch of symbols and algebra, and then you'll get like something like this. If you haven't got something like this written somewhere and like put like a big box around it, you're like, cool, I've proved these results, these formulas, and now I can use them. However, as I mentioned before, right at the top, right, being able to use a formula is no substitute for understanding where it comes from, because that's actually the thing that matters. I'm pretty confident that the vast majority of you, no, actually I take that back. I'm pretty confident that not one of you, after you leave school, is going to need to go back to these things unless you become a mathematics teacher. Explicitly anyway. Even those of you who become, say, engineers or go into finance or those kinds of things where you will use these results all the time, you will get a computer to do these things for you. You do not have to be able to do these by hand. And you might say to me, Mr. Wu, why are we wasting our time doing these then if I'm not going to use them after school? And the answer is you are, just not as these formulas, right? It's really the thinking and problem solving process underneath that really matters. In much the same way that no one's going to stop you on the street and hold a gun to your head and say, tell me why Macbeth's literary techniques are going to be the reason why Shakespeare is a part of English history. They won't do that, at least I really hope they don't. But it's your understanding of text and characters and plot, they will matter. And hopefully those will be things you enjoy for the rest of your lives. So I want to dig into this one result in particular because this is the part that really matters. Not the formula, but the thinking that goes along with it. Two parts. Number one, you may recall, and you've got it written there in your books hopefully, I rubbed it off because I needed some more space, as you can see. We pulled this move in the middle of trying to, there's like 4 or 5 lines of working here, and at a certain point we saw this on the numerator of the quotient rule. Do you remember that? And we were like, gross, but most of you remembered, oh, I can simplify that as 1, okay? Now this thing here is an important trigonometric identity, but I would like a show of hands, and don't worry, I'm not going to ask you to actually say it, I just want an indication. I'd like a show of hands for who could tell me, I won't make you, but who could tell me why this is true? Any takers? 1, 2, 3. Okay, thank you, hands down. I'm glad it's not 0, but it's got to be better than that. So here's what I'd like you to do with me. Pick up your pen. And the first thing we're going to do is understand why this is the case, because it's super important. If you're just using formulas without knowing where they come from, you are not a mathematician, you are just a machine. Taking symbols, turning them into others. We have better goals, higher goals for you. So, if you can draw just a couple of basic right-angled triangles for me, I want you to think about, like, way back when you first met the trigonometric ratios. In fact, we called them ratios, not functions, because they were about comparing sides in a right-angled triangle. That's what ratios are. Divide this thing by that thing. Okay? So I just want you to rehearse with me. Each one of these, sine, cos, and tan, is a ratio in a right-angled triangle. You even have a whole mnemonic for it, right? SOHCAHTOA. What is sine something over something? What is it? It's opposite on hypotenuse, right? And you can keep the SOHCAHTOA going. Cos is going to be adjacent on hypotenuse. And then lastly, tan is opposite on adjacent TOA. Okay, great. Right? Now, we can visually represent this on our right-angled triangle by saying, if here's the theta, here's the angle we're interested in, opposites over here, adjacent's here, and there's the hypotenuse. Okay, now where this result comes from is the result of asking a very simple question, which is, this hypotenuse here, what if we had a hypotenuse that was equal to 1? What would that look like? Is that important? Well, let's see. When you do sine and cos, and that's actually all we will need for this one, when you do sine, instead of just saying opposite on hypotenuse, you can say it's opposite, this side, divided by, well, I've just said, like, what if the hypotenuse is 1? So it's just 1. Do you see what I just did there? If the denominator is 1, then the sine is equal to the opposite side. So instead of writing opposite, I'm just going to write sine here. Is that okay? Sine is, that's weird, because we would normally think of this as like something to do with an angle, but it's a length now, right? Same deal with cos. If the hypotenuse is 1, then what is cos equal to? It's a over 1, which I guess you could just write a, right? That's the adjacent side, so that's cos down here. Now, if you look at this and you apply Pythagoras to it, you get the result that we looked at before, right? A squared plus b squared equals c squared. Or, I mean, you can write it whichever order you like, right? A squared plus b squared, there's the sum of the squares of the two shorter sides, equals the square of the hypotenuse, which in this case is just 1. And that's where the result comes from. It is essential that you know not just that things are, but why things are. So that's the first thing that I wanted to pull out. And the second one, I did ask you to put your laptop down before. You could put it up for this part if you wanted, but I'm going to show you everything you need to. I'm just going to ask this question. Like, we got this result. And my question to all of you is, and? Like, so, why should I care? What does that even mean? What does it look like, right? I want to show you why, and again, we're going to do this just the way we did with sine and cos. Why, visually, when you look at this thing, you have to end here. There's nowhere else you could go, right? So let's have a think about, what is that? Sec squared x. It's a reciprocal function. What's sec the reciprocal of? It's cos, right? So let's put cos on here. Hopefully you can see that, right? Now, it's not just cos that we have, it's actually cos squared that ended up on the denominator, right? Cos squared. So just look at it for a moment. Again, think visually. What's going to happen to this? And I'll restrict it just a little bit to make it easier to see. What's going to happen to this thing when you square it? When you square this graph, what would it even look like? Well, you can think about some of the values. Like, see this 1 squared is 1. So when you square this, you'll be going through there. This is 0 down here. 0 squared is 0. So you're going to be there. What's this value down here, vertically? It's -1, right? Can you see it? Sorry, it's not the most obvious, but my iPad's in the way for some of you. But -1 squared, -1 times -1 is 1. So you're going to be back up here. So you're sort of like here, and then you back up here somehow, and then there's this symmetry to it. So does it make sense to you that if you were to take, not cows, if you were to take cos x and then square it, you should get something like that? Looks weird, but are you okay with why it is what it is? You can see it's all positive because it was squared. The spots that were 0 become 0. The spots that were 1 and -1 become 1. So now we want to go from this to its reciprocal. Right? This is cos squared. This is 1 divided by that. I'm going to get rid of this one. Right? There's cos squared now that we're focusing on. Okay? Again, have a think. 1 divided by this. What's 1 divided by 1? 1. What's 1 divided by a half? 1 divided by half is 2. What's 1 divided by 0? Uh-oh, we got problems there, right? So whatever this graph is going to look like, it's going to have some weird spots, okay? So now I'm going to go 1 divided by, here's cos x squared. That guy's weird. But does it make sense? Can you see why? Like there's a spot 1 that you told me 1 divided by 1 was 1. Here's a half. In fact, I can even prove it. If I go x equals 0.5, there it is. And you can see right there, oops, no, sorry, not x equals 0.5. How am I going to do this? I think it's like 0.7-ish. That's not bad. There you go. I'm getting closer there. I didn't get exactly on half. Sorry about that. So you can see it's this weird shape to it. Why is there a break here? Do you remember why there was a break? I asked you this point down here. X equals 0, you can't divide by 0, right? So in fact, there's an asymptote going right up through here, okay? So this is what that is, sec squared. How is that the derivative of tan? Are you ready? Here comes the clincher. Let's put tan on. All right, there's a lot going on here, so let's restrict it a little bit so you can see. I reckon that'd be enough. 0x. Okay. It's not restricting the way that, because I typed it on the wrong spot. Because you're an idiot. That's better. There we go. You're also patient. Thank you. All right, that's more like it. Look at the tan curve. It's the one in black. Can you see it? And we've seen the tan curve before. I didn't ask you to draw it, but have a look at it. There it is. It's familiar, I hope. When you draw it in there, it's got this upward curve. What does that mean for the gradient? The gradient should be positive, right? So that's why this green graph is always positive. The lowest that the green graph goes is 1. And that's because when you have a look at a spot like, say, there, right there, that's a gradient of 1. You could do the same thing with your ruler that we did earlier on and place that there, and you get a gradient of 1. But the rest of the gradient, well, tell me when you have a look at this tan graph, right? What can you tell me about the gradient when you move towards the right? Does the gradient get bigger or smaller? It gets bigger. It's like steeper and steeper and steeper forever. And that's why this gradient, the green graph, gets higher and higher and higher. Does that make sense? So this is not just what the algebra gives you, it's what the picture tells you, and that's the important part of this, okay?